large group notes on galaxies and the beginnings of our talk about the universe. So you can kind of think of our universe as structured by how the different pieces fit together. So if we think about things from smallest to largest, really planets, there's other smaller objects like comets and asteroids, of course, but if we start to think about like bigger structure, the smallest we're going to go here in this class is planets. We already know that stars are bigger than that. And then if you put planets together with stars, you get solar systems. And so you have to have both planets and stars in order to have solar systems. Lots of stars together, with or without planets, make galaxies. Galaxies can then be clustered into galaxy clusters. And then, of course, then you have your universe. So those different pieces all fit together, and we're going to focus in on this section right here in terms of galaxies. And so when we start to think about this, the universe contains hundreds of billions of galaxies, and galaxies contain hundreds of billions of stars. So we often get the question, like, do you think there's life out there? The thing is there life on other planets is possible. It's just that if only one planet in each galaxy had life, and if there was all of those billions of stars in each of those billions of galaxies, the probability of finding it is 1.0 times 10 to the 22nd. So that's hundreds of billions times hundreds of billions. And so life being out there is highly probable or possible, but it's probably not likely that we're going to be able to find it. And so the odds that you're going to see an alien or another ship are probably pretty low. All right. So the other thing we need to think about when we're thinking about finding it is distance. Those distances between things are super big. And how do we measure those? So there's a couple of factors that come into play here. We need something to be able to measure with, and those are called distance indicators. And so those are things that we know the absolute magnitude. And so when we know the absolute magnitude, we can figure out how much it's been dimmed because of the distance. And so those are what we would then use for like the rulers of the universe. And then the other thing we need to think about is look back time. When we look at light coming in from those other objects, it has taken light time to get there. So it's kind of like a pre-recorded text or a pre-recorded voicemail. That came at a different time in your life than when you're actually reading it. And so same thing works for the light that we see coming from other objects. And so we're looking at that light as it was when it left that galaxy millions of years ago, and it's like looking back in time. So when we go to measure units in the universe, we have several units that we're going to talk about in class. You've already seen that the unit AU, or astronomical unit, go by. And so that's only used for distances within our solar system. And so that's the average distance between the Earth and the Sun. So the other one we've already talked about as well is the light year, which is the distance light travels in 1 year. So we use that for nearby stars within our galaxy. And again, don't write these numbers. You can always Google them. The next one, bigger one, would be parsec. These would be stars still within our galaxy that are a little bit farther away. So that's about 3.26 light years. Megaparsec is where we get outside of our galaxy, so between galaxy clusters and different galaxies. So 1 megaparsec is 3.26 million light years. And so we need to talk about numbers here a little bit, because it's hard to think about these things when we start to think about millions of miles or millions of light years, right? And so it starts to get what we call fuzzy numbers. Your brain really can't wrap around that. And so even if you start thinking about how big is a billion versus a million, we don't really have a good concept of that. So if we think about it in something we do have a concept of, 1 second, right? 1 million seconds is only about 11 days. But 1 billion seconds is about 31.5 years, 31 and a half years. So when we start talking about making these differences in distances, you're really making a significant jump between those different distance factors. So that's one of the reasons why we use those different units, is so that our tiny little human brains can wrap around it. You are going to see here popping up this video, a link to this video. It's really helps you start to see how they put all those pieces together to measure our universe. So I will link to this video here and at the end of this particular one. So then, once we start to know distances in our universe, what's really cool is we can figure out how old it is. Because we know the speed of light and we can figure out how far they are, we know how much time it would take light to go that far, and so we can infer how old the universe is. And so we know that it's 14 billion years old. The other interesting thing about that, we're going to learn more about this later, but that also means that there is an edge that we can't know past. We can't know what's happening beyond an edge. Once we start to talk more about how our universe is changing over time, we'll get into that a little bit more, but there is an edge somewhere that we haven't found where we can't learn what's going on outside of that edge. We need to know more first before we can talk more about that. So we're going to talk about different kinds of galaxies here for the next couple of minutes. The first kind we're going to talk about is the one we live in, spiral galaxies. They are just a spiral. So there's a spot in your notes for you to write how old those stars are, how frequent they are, and then to write pictures of those. So they are literally spirals. They have arms. They're kind of overall roundish shaped. They have arms that sweep outward, and they make up 30% of all galaxies. So you do not need to know this breakdown. This kind of just represents the center. So in your pictures, you might include one that comes, from a roundish center, or one that comes kind of from a straight line or a bar. And they will tend to spin faster in the center, and they contain both young and old stars. So on your notes, where age of stars, I wrote young and old. And then percentage of all galaxies, I wrote 30%. And then I'll show you some images here in just a second for what I drew. So our Milky Way galaxy is probably the best example, and that's why we started with this one. We know that it's 100,000 light years across. It's about 10,000 light years thick, and we're about 2/3 of the way down one of these 3 splintered arms. And then the other thing that's hard to remember is everything in outer space is 3-dimensional. So there's actually like a spherical halo or bubble of stars and gas and other material that exists around the Milky Way. So some images of what our Milky Way could possibly look like. This would be looking at it from an edge, and you can see the nucleus. This one has more of a boxy nucleus in this particular image. This is not our Milky Way. This would be an artist rendition. So ours we know to be a little bit rounder than what this image shows. Here's another one. If you Googled Milky Way, you might pull up this image. This one shows a bar in the center. So remember we said some of those spiral galaxies are from a bar. So here's an example of a bar. Again, ours is more of a round nucleus there. What I do like about this image is you can see the splinters. So if I chase this down, I can see a fork in the road here, and it splits, and then it splits again, and then it splits again here. And so we would be about 2/3 down a splintered arm like that. So I do like the splinteriness of this one because that really is a good representation. Here's another example. The nucleus on this one's very good. The splitting is very good on this one. You'll notice all of these are different colors, and these are all because they're artist renditions. And the reason why they're artist renditions is, let me think if we think of it a different way. Could you see the shape of the forest if you were standing in the trees? You can't really, right? Because you're inside of it. So we have to infer what the outside of our galaxy looks like based off of other information. So the next kind of galaxy we're going to talk about is the elliptical galaxy. These can be, from what we already studied in Kepler's, they can be very ovalish, they can be very circlish. It depends on also our frame of reference, if they're tilted or not to our frame of reference, and also because of their eccentricity. Most of them are small, but some of the largest known galaxies are elliptical. They make up 60% of all of our galaxies. And so their main defining features, they're round. They don't have arms or bars. And they are composed of old stars. So on your notes, you would write old where it says age. 60%, and then you draw different kinds of ovals with maybe a dot in the center because they do have some concentrated stars in the center. So here's a good example. You can see how round this galaxy is. This one over here is a spiral. You can see the arms. This one up here is kind of not sure which because we can see that it is round, but are those spiral arms or not? So the angle at which we see a galaxy really impacts what shape we believe it to be, and then we would need more information. But you can see kind of how round this one is. It kind of goes all the way out here. So then the last kind of galaxy we have are irregular galaxies. They make up the last 10% of all galaxies. These again are young and old. So the only galaxy that was really different was elliptical, and how I remember that elliptical are old only is because the letter O is an ellipse. So old for ellipse, that's how I remember that one. And so irregular galaxies really have no shape, so I'm going to actually scribble in my notes for that one. There's two that we can see in the southern hemisphere, so if you ever travel to the southern hemisphere at all, you can see the large and small Magellanic Clouds. And so what's cool about these is they really look like those nebula pictures that we saw when we were studying stars. But the thing to remember is these are much, much bigger in size than those nebula are. And so there would be nebula inside these galaxies, several billion nebula inside these galaxies. So they're huge. So there's a little fun link you can try. We actually wrote the word Earth space science there, and you can see all galaxies are represented, and you can make your own at this website here. So that's kind of how galaxies work. But the interesting thing about galaxies is we use those to then learn more about our universe. So if a group of stars is a galaxy, galaxies are grouped into clusters. So a group of galaxies is a galaxy cluster. They can contain thousands of galaxies. Our cluster that we live in is called the local group, and we have 28 identified galaxies so far. We can also group these galaxy clusters into superclusters, and we think those are the largest piece. And so what's really cool is when we start to look at galaxies and galaxy clusters, we find things like collisions happen. So how do we get those different kinds of galaxies? And so galaxy collisions is how we think we got those three different shapes. But the thing to remember is galaxies collide, but stars don't. Stars within their galaxies are spaced really far apart. So think about it as like crowds of people moving through a space. So if you had a bunch of people leaving one space and then a bunch of people going into that same space, you could pass through that crowd and you wouldn't really crash into another human being. Stars kind of work that way. So the crowds themselves collide, but the people inside them don't. So galaxies work that way. But what will happen is that gravitational interaction between those two pieces will happen. And so galaxies can steal gas and dust from each other that way, and they call it galactic cannibalism. That's kind of cool. Astronomers aren't very creative, but it's pretty fun. And so they last quite a long time. And so that's one of the other reasons we look at these large and small Magellanic Clouds. So this is the Large Magellanic Cloud, and the dots themselves that you see, the red and blue dots, are stars that were actually stolen from the Small Magellanic Cloud. And so the proof that we have is they have different kinds of rotation than what's already there in the Large Magellanic Cloud. It's opposite. They have weird orbits that aren't quite the same pattern as everybody else, and they have a different composition, and those all match the Small Magellanic Cloud. Kind of a fun aspect of study. Another interesting one we have is the Cartwheel Galaxy. Cartwheel Galaxy here is this one in the center, and we think both of these collided with this guy. And so the evidence is these are all supernova going off, that kind of exploding. You can start to see the spiral shape reforming here. So this is a close-up of the centerpiece. This is a close-up of those nebula on the outside of those supernova. And so you may actually, those supernova going off may actually also cause star formation out here. So kind of a cool, interesting piece there with that galaxy collision. All right, so hopefully we learned a little bit about what makes our universe structure happen, and then we'll look at how our universe is changing then in our next video.